Hi there, statistics students. We are going to take a look at this neighborhood of 10 houses, and now we want to understand what standard deviation tells us. So we have the value here, this 3.6286 if we're going to round to 4 digits. Well, what does that 3 and a bit mean? And as a reminder, folks, this funny sigma x, that is your calculator's best attempt to be like, oh, let's see, you entered in some sample data. Let me give you the standard deviation for the whole population. You're like, that's impossible. You're crazy. So never, ever, ever use sigma x. We will use SX, the sample standard deviation. Okay, so 3.2686. Let's see if we can understand what that value is. So here it is. Let me go ahead and make this value, write it down, take a note. This standard deviation was 3.6286 from our output. And then we're like, yeah, I don't know what that means. So let's see if we can figure out what that is. Now this formula looks absolutely terrifying. It's got this Greek symbol, it's got subscripts, it's got bars, it's got square, it's got all this stuff going on. We need to break it down. We can expand this into a formula that looks a little bit less ridiculous. Let's see, I can make that just a little bit bigger. This tells us what this funny looking E thing is. This means a sum of this kind of pattern of things. So now I want to take a look at what is this pattern of thing that we're looking at, because it's a repeated pattern. What this guy says is that take the first house, which had 0 people in it, and compare it. That's what a subtraction means. It means compare, or what's the difference? Compare to the average. We may need to remind ourselves that the average was a 3.5 person household, right? Which can't actually happen. It's a measure of if all the households, all the 10 houses had to have an equal number of people, how many people would it be? And of course, we're not really going to do that. So now we're going to compare every single household to this concept of average. So this very first guy says, let's compare the household of 0 people to the average household. Okay, and then it says, let's add that to, let's compare the second household. Let's compare the second household to the average, so on and so forth until it's all the way. This N would be 10 since we have a total of 10 houses. Then we'd say very last, keep doing that pattern, adding them together until we've compared this last household to our average. So we've compared all the households to the average household, and then take a look at every single one of these says square it, square it, square it. All that does, if you square a number where the negative or positive, makes it a positive number. This is because we are going to do a comparison here, and it doesn't make sense to have a notion of distance is really what standard deviation is about. It doesn't make sense to have a negative distance or negative comparison. Then we add all those up. So oh my gosh, this formula is looking so crazy. But it does the thing where it says, all right, compare the household to the average, add them all up, and then divide by, it says this is about how many there are, right? And n-1, that's not quite how many there are, but where else have we seen an add them up and divide by how many there are? It's the concept of average again, where you add them together and then redistribute. It says, okay, well, we've compared every single household to the average. Now let's kind of like redistribute that so that everything's fair. It's like, okay, now let's compare the houses, like how different are they from the average? And if they were all going to be the same amount of difference, how different would those households be? The square root here, this square root of this whole crazy business, that's the craziest square root ever. It's kind of the mathematical concept of like, hey, look, you squared things, you've made things much bigger, now let's take them back down to scale. But folks, all this does for us is it says the interpretation is this. The households are 3.6 people. The units here are what we're counting. So if instead of people and houses, this was oh, I don't know, how much something weighed in ounces, then you'd be like, it's 3.6 ounces. The units of measurement are what the variable is. So we would say there are 3.6286 people, either more or less than the average number of people in the houses. And Briona's, I forgot how I spelled her name. How did I spell her name? Brioni. I saw that name the other day and I was like, that's such a pretty name. Brioni. Okay, in Brioni's neighborhood. Okay, more or less. It's a comparison to the average. Okay, so if all the houses had to have about the same difference. Okay, now I feel like this is not as easy to understand as another way of thinking about this standard deviation, this 3.2686 people. You're like, bang! So here's what we've done next. We can say, hey, this interval, when we go average, add, or subtract a standard deviation. So let's see, that was our average was 3.5, and we either want to add or subtract, and then we're gonna have to do that in two separate calculations. There's not an add subtract button, but there's an add button and a subtract button. But if we go 3.5, both add and subtract this 3.6286, we end up with a low number. When we subtract, we end up with a negative 0.1286. I did this calculation earlier. You can check my calculations. And on the high end, we end up with 7.1286. In other words, our interval is the range of values in between negative 0.1286 up to the value 7.1286. And you're just like, yeah, so what? Well, let's go back to both our raw data and our histogram. So if we go all the way back, this is our data, this is our histogram. I'll go ahead and copy them over so that we've got everything in one place. Maybe, click. Here's what we can see on this. This little interval, I can capture this right on my number line. It's kind of like drawing a big circle around the interval. It could be like, okay, well, there is on this side, the negative 0, you're like, that's on this end. And positive 7, well, that's a little bit bigger than here. It's kind of like this is what's typical. Okay. So let's go back just a moment. Typical. Most expected, that is what to expect. When we were talking about average, we made a big deal about saying there's a misconception that average is typical. No, it's not. What is typical, how we understand things, is the average, add or subtract a standard deviation. And so we can say the average plus or minus a standard deviation. We can say the typical number of people in Brioni's neighborhood is, well, you can't have negative people in our context. I mean, if this was talking about weight or something, you could be losing weight or something like that. But this is people, is at least 0 people. But not more than 7, or like up to 7 and including. And if we go and we look at our data again, right, all the way back, we can be like, for typical households, well, shoot, that's just about all the households except for this one mansion over here that we already identified as an outlier. Okay, so we can say typical is the same as saying most of the houses in this neighborhood have 7 or fewer residents. There might be the odd one out, but it was rare. Now there is only one last point. This interval, this low and high, or the low end of the interval, the high end of the interval, is not the same as test for outliers. So let's just make sure we say that this interval is different than testing for outliers. And let's just prove that mathematically. If we go back where we were looking at outliers, our high outlier cutoff was 11 and our low outlier cutoff was -5. They gave different values versus our interval, -0 to +7, not the same thing. In other words, our range for what we're considered typical is narrow, and outliers, to be considered an outlier, you got to be like way out there. All right, so we're done with this description.